Okay, so yesterday we went over the basics or the fundamentals of vector addition, right? And that is that we represent vectors with an arrow. Okay, the length of the arrow represents the magnitude of the vector. The arrow points in the direction the vector is supposed to be going. All right, so those are things we have to remember. At the end of the day, we worked on a problem where we had an object that went, or a person I think was walking away from a campsite, and they went south a little bit, then they went east a little bit, and then they came back north a little bit. Okay, and we said that their resultant was this line right here. Okay, that line represented their total displacement over the whole trip. In order to find that, we had to make a triangle for it. Okay, and so what we did is we said that during this whole trip, the person ended up, I think this was 1.2 kilometers. They ended up 1.2 kilometers east of where they started. And they also ended up a half a kilometer south of where they started. Okay, when we did that, what we had probably unknowingly done is we had found the horizontal or x component of our displacement and the vertical or y component of our displacement. Okay, anytime we have a vector, that vector has a horizontal and vertical component to it. That's why we can always build a right angle triangle from any vector quantity we're given. Everyone following me so far? So what we're going to look at today is how can we calculate those vector components and how can we use them to add vectors that are not perpendicular and not collinear, because that's what we looked at yesterday, was ones that were perpendicular, ones that were collinear. What we're going to look at today is going to be something like this. Oop. So we would be able to add these two vectors together. Okay, so if this object went 10 kilometers, okay, at 40 degrees, which way would this be if this is a compass? East of north, okay, and then turned and went 4 kilometers at 30 degrees west of north, okay, what would be its total displacement? This is what we're going to be able to do by the end of today, okay, is calculate its total displacement. The way we do that is, first off, obviously we draw a line that represents the total displacement, which goes from beginning to end. Okay, now this applies again for any vector quantity. Okay, all vector quantities are added in the same way. This happens to be displacement, but if I'd have done 10 meters per second and 4 meters per second, I would be calculating the average velocity or resultant velocity. If these were two forces, I would be finding the net force. It doesn't change what I do. Okay, and in fact, in period 3 yesterday, I had someone say, but Mr. Coderre, that's not how forces work. Okay, if two people push on the same object at the same time, it doesn't work the way you're saying. And I said, okay, come on up here and I'll prove it to you, okay? Because he was just visualizing it differently. And so I thought, you know what, it ended up being a pretty good demo. So I want to repeat it with you guys here, okay? So, David, can I get you to come up here for a sec? If I'm looking at two forces, okay, and I'm going to have David stand on this side of the desk, okay? David's going to push the desk this way. I'm going to push the desk that way. Which way is the desk going to go? Right, diagonally, right? If we draw that, okay, in terms of the two forces, we'll have David's force and we'll have my force. Okay, if I draw them tail to head like I'm supposed to with any vector quantity, the resultant is the direction the desk should go, the net force of the two forces, all right? So you can push that way, I'll push this way. Okay, moves diagonally, right? But he was envisioning something else. Okay, I'm not sure exactly what that was, but a lot of people, once they saw that, had an aha moment. I don't know if everyone else had that, but it was, I thought, worth doing it. Thank you, David. Okay, so works for any vector quantity. Now, for these two here, okay, my blue line represents my total displacement. In this case, the total displacement ends up being some distance north and some distance east, okay? it has a vertical or north component and a horizontal or east component. Everyone okay with that? All right, so here's where we want to get to. If I take the north or vertical part of my 10-kilometer vector and I add it to that one, do I get the total north component? Yes, I do. Okay, and the same is true for the east and west ones. If I take this line here and add it to this line, this one's west, so it's negative, okay, they add up to this one. So what we're going to be doing is looking at how do we break vectors up into their horizontal and vertical parts so we can calculate what the resultants vertical and horizontal parts are. Exactly, yes. If not a right angle triangle, it doesn't work. Yeah. Okay, because it doesn't make, yeah, no, it looks kind of like it is there because of the way I've drawn it, but it's not. Yeah? Okay. All right, everybody all right with that? And even doing that wouldn't give me the vector, right? I would still need the vector after that, which would require me to do this whole step anyway. Okay. All right, questions on kind of where we're headed there? Okay, so that's what we'll be doing is learning how I can take this 10-kilometer vector and find what we call its y and x components, horizontal and vertical. Okay, and same for the 4-kilometer triangle here, how I can find its vertical and horizontal parts. Okay, if I add all the x's together, then I'll get my resultants x component. If I add the two y's together, I will get my resultants y component, and then I can do Pythagoras, and then I can do trig, and I'll have the numbers. Oh, that is the right triangle? That is, yeah, I know they don't look like it because I don't draw well. Yeah. Okay. These are all right angle triangles. This doesn't work. Yeah, they all are. Okay, this doesn't work unless they're all right angle triangles, right? Trig doesn't work that way. Yeah. Okay. So if we know the magnitude and the direction of a vector quantity, which we should, it's a vector quantity after all, we should always know those two things about it, okay, then it's possible to find the horizontal and vertical parts of it using trigonometry, right? So if I know how big A is, and let's just say it's 300 meters, okay, and I know what direction it's going, let's say it's 40 degrees north of east, can I figure out how far east it goes? Okay. Yesterday we talked about the three trig functions, sine, cos, and tan. Okay. I know the hypotenuse, and I'm trying to find this side, which is which side? Adjacent, opposite, or hypotenuse? It's adjacent, right? It's touching the angle. It's beside the angle. All right. Which trig function deals with the hypotenuse, an angle, and the adjacent side? Cos, right? So, ka, toa. Ka is the one we're dealing with. Okay. C-A-H. Right. So if I use cos, okay, I can say that the cos of theta equals the adjacent side divided by the hypotenuse. Right? So I know theta, 40 degrees. I know the hypotenuse is 300 meters. Can I solve for adjacent? Yeah, it's not a hard manipulation, right? I just bring hypotenuse over here. All right, so mathematically, that'll look like this. 300 meters times the cos of 40 degrees. Okay, so when I do that, okay, all right, so it's telling me that that side is 229.81 meters long. Okay, and that sort of makes sense. It should be shorter than the hypotenuse. Agreed? Okay. So now I know that the x component, or the horizontal component, is 229.81 meters. Obviously, I would keep all the decimal places if I was doing anything else with that number. How would I find the other one? Okay, I could do Pythagoras, but that tends to not be quite as accurate. Trig functions tend to be a bit more accurate because I'm not subtracting. Okay, what trig function will find me the opposite side if I have the hypotenuse and the angle? Sine. Right, so I can find that side by going sine of 40 degrees equals the opposite side divided by the hypotenuse, which is 300 meters. All right, so I do the same calculation kind of that I did here. 300 times the sine of 40 equals the opposite side. Now, given that angle, should that side be longer or shorter than 229? Shorter. It's a 40-degree angle, right? So that side should be shorter. If it was 45, they'd be the same. Okay, so always a good way to kind of mentally check if you've done it right. All right, so when I plug that in, okay, I'll have the sine of 40, okay, times 300, and that side comes out to 192.84 meters. Okay, so now I have the vector components, the x and y, or the horizontal and vertical components of that vector. Okay, was the math very hard to get there? I mean, really, I just have to remember what trig function to use for each side. The adjacent side's always cos, the opposite side's always sine. Okay, all you're doing is multiplying the sine of the angle or the cos of the angle by the hypotenuse. Okay, and you'll always get that other side. They're ratios. Okay, so anytime you change the angle in a triangle, you change the length of the sides, right? If you increase the angle, the opposite side gets bigger, the adjacent side gets smaller. And cos and sine just work on the ratio between those sides based on the angle. Okay, that's why we call them simple trigonometric ratios. They always work on, if the angle is this much, here's the ratio between x and y. Or, sorry, x and y. Yeah? Okay. All right, everybody okay with that? Okay. So this is kind of what we just looked at, okay? The adjacent side is always going to be calculated using cos, okay? The opposite side is always going to be calculated using sine. Does that mean y will always be using sine? No, it depends on how you draw the triangle, okay? Sometimes the opposite side could be the horizontal component, could be x. It just depends on which way the triangle gets drawn, right? If we drew the triangle this way, right, then I would be calculating y here using cos, because now it's adjacent to the angle, and x is opposite, so I'd be using sine to calculate it. All right, so I just don't want anyone to think that, oh, yeah, x is always cos and y is always sine. It's not. All right, questions so far there? I know right now it's going to seem a little bit overwhelming, but once we do a few, okay, you'll go, oh, these take forever, but you'll get better at them and they'll get faster, and it's always the same steps. Okay, that's the nice thing about doing vector addition this way. Once you learn the steps, you can do any vector addition question because they're all the same. Okay. All right, so this is what we just did. Okay, we did the calculations, except we had a different number. I used 300, and okay, they used 175, but okay, same calculation we did here just a minute ago. All right, so this is what I was trying to show you with my crude drawing a minute ago. Okay, if I want to add vector A and vector B here, okay, and figure out what the total displacement is or what the resultant is between those two, the resultant would be C. Everybody all right with that? It goes from beginning to end, right? That means C has a triangle that looks like this, all right? And I can calculate these sides if I can find how far over A goes and how far over B goes, because if I add those together, they add up to how far that goes over in total, right? And it's the same for the y's. If I take AY and BY and add them together, okay, I get how far up we go in total. Okay, so we're just taking the individual pieces of the two vectors and putting them together. That's why we call it vector addition. We're always putting them together, okay, to calculate our resultants, x's and y's. Questions there? All right, and then we already explained that. So here's what I want you to do. I want you to copy down this example. Okay, and we're going to walk through it step by step on how to do vector component addition. And I'm actually going to remove this diagram and I'm going to redraw it myself. Okay, so just write down the question for now, and then I'll walk you through all of it, including drawing the vector diagram. Anytime I'm adding two vector quantities, how do I draw them? Tail to head. Okay, so that means draw the first one and then draw the second one on the head of the first one. Okay, so I'm going to start out with my first one here. It says it's 145 meters long and it's oriented 70 degrees from the horizontal. So I just want to draw a line that's horizontal Okay, and I'm going to go 70 degrees above that. So it's going to, I drew that way too long, but okay. So 70 degrees would be something like this. Okay. So there's my 70 degrees, and it's 145 meters long. All right, there's my first vector. Okay. How did I know where to draw that 70? Right, it said from the horizontal. That's like saying north of east. I know to measure it from east if it tells me that. Okay, in this case it said from the horizontal, so I knew the horizontal was my reference. I could draw it the other way if I put it at a 20-degree angle. Yes. Okay, like I could have drawn this triangle like this and said, here's a 20-degree angle. It would be the same. Because it said above, right? Oh, I assumed that horizontal meant the positive horizontal and not the negative horizontal. Yeah, okay. I made an assumption there. I think it's probably a safe assumption. If they wanted me to go the other way, they probably would have said the negative x-axis so that I could be sure. Okay, no, that's a good point. Okay. Then the next vector has to start here on the head of the first. And it tells me that that vector is 105 meters long and is 35 degrees below the horizontal. So again, I'm going to draw a line that's horizontal as my reference, and then I'm going to go 35 degrees below that. Okay, now that I've got those two vectors drawn, I want to label their horizontal and vertical parts. Okay, this is the horizontal component of my 105 meter long vector. Okay, this is the vertical component of that vector. Similar for the first one. This is the horizontal component. This is the vertical component. Okay, so I always want to label my x's and y's so I don't get them mixed up. All right, where would I draw a line that would represent the resultant here? In this case, the resultant is the displacement. Right, from the start to the end. So I would start right here, okay, and I would go to the end of the 105 meter long vector. All right, so that is my overall resultant. In this case, the resultant is displacement. It also has a horizontal and a vertical component, and it also has a vector. I don't know what that is, okay, but I'll be able to find it later. And like I said, it represents the total displacement. Now, a diagram like this can start to get a bit busy. Okay, there's going to be a lot of stuff in there, right? Once we're kind of a little better at the fundamentals, I'll show you another way to draw it that doesn't make it look quite as busy if that really bothers you. Okay, for me, I like drawing them this way because I can see the whole picture. I know what I built, I know what it results in. Okay, the other way that I'll show you later, okay, you can't see the end result until you're actually finished, and that makes me insecure, and I don't like that. Okay, so I'll show you that way later, but for right now, this is the diagram we're going to use. So looking at this diagram, if I add red X and black X together, will that give me blue X? Okay. Similarly, if I add black Y and red Y together, will that give me blue Y? It will, as long as I make red Y negative. And it is, right? It's downwards, and down is negative. All right, so as long as I know that, then what I need to do is start doing some calculating. I need to calculate what all the X's and all the Y's actually are. How long are they? Okay, that's my next step. So I've got the diagram drawn. I know what everything's going to do. Now I calculate all the X's and Y's. So first thing I want to calculate is black X. All right. What side of this triangle is black X? Adjacent, opposite, or hypotenuse? It's adjacent. Okay, I know how long the hypotenuse is, and I have this angle, so I can calculate black x. Okay, I'll calculate black x by going the cos of 70 degrees times the hypotenuse, which they told me was 145 meters. Okay, so here's what I did in order to arrive at that, just so no one's lost. Okay, the cos of theta equals the adjacent side, which is x, divided by the hypotenuse, which in this case is 145. Right, so all I did was manipulate to solve for adjacent. So I brought the hypotenuse over. Everyone okay with what I did there? All right. All right, so we got the cos of 70, okay, times 145. All right, so that side is 49.593. We're going to keep all those decimals. I'm not going to write them all on the board, but we'll keep them all in the calculator. Okay, I'm going to write 49.59 up here, just so I have it. Meters, and which direction is that? Positive, yeah. That's really all we can apply, right? They told us horizontal. It's horizontal and it's that way. So we'll say that's positive because right usually is, right? So just going to say positive 49.59. All right, now I also want to calculate black y. Okay, black y is the opposite side of this triangle, so I'm going to use sine for that. Sine of 70 degrees times 145 meters, right? So similar manipulation here, okay? The sine of theta equaled the opposite side divided by the hypotenuse, so I just manipulated for the opposite side here. Should this side be longer or shorter? Longer. Yeah, 70-degree angle, opposite side's going to be bigger, right? And if we look at our triangle, it says that too. Okay, so this is 136.25, I'll say 255 here. And that's also positive because it's up. Okay, so if I'm looking at my triangle here, this is the side I just calculated, all right? And it's definitely longer. But that's why, again, scale is somewhat important. As long as I make sure my diagram is at least somewhat to scale, I can confirm my numbers by looking at the diagram. I'll know if I accidentally switched them or not. Okay. All right, so everyone follow what I've done so far? Okay, I've just calculated the two sides of the black triangle. Now I'm going to calculate the two sides of the red triangle. All right, so in the red triangle, x is, again, which side? Adjacent or opposite? It's adjacent, it's touching the angle, right? So I'll use cos to get it. Okay, so I'm going to go cos of 35 times the hypotenuse, which is 105. All right, so we got 86.01 there. Meters, and that's positive. Okay, it's pointing in the same direction as the other x I had, and it was positive, so it's positive too. Okay, and again, our y component is opposite the angle, so we're going to use sine to calculate it. So I'll take the sine of 35 and multiply that by 105. Okay, and this one should be shorter. Okay, y should be shorter than x in this triangle. Okay, so there's all my numbers, 60.23 we'll say. Positive or negative? This one should be negative, okay? This y is pointing down. This x is pointing to the right, okay? This y is pointing up. This x is pointing to the right. So to the right is positive, up is positive. Because this y component is downwards, it needs to be negative, right? Okay, so now I've got all the x's and all the y's. So we said before that if I take red x and add it to black x, that'll tell me this side of my resultance triangle. All right, so that's my next step. I want to add the x's together and add the y's together so that I can get what the sides of my overall triangle are. Then I can do Pythagorean theorem and I can calculate the vector once I have those sides. Okay, so next step. Okay, so I'll take black x, which was 49.59292078, and add that to 86.01. Oh shoot, I lost my other one. Okay, so 135.603. Okay, obviously I'm going to keep all those decimals. I'm just not writing them all. Okay, so I know that in total, this object, whatever it was, goes 135.603 meters along the positive part of the x-axis. Okay, everyone all right with that? All right. If I'm going to calculate blue y, then I need to add the two y's together. That's 136.255 and 60.23, but the 60.23 we already said is negative. Okay, so I'm going to go negative 60 point. Whoop. I wanted that. Okay, and then I'm going to add it. I lost my full number there, so I'm just going to do that calculation again, just so that I get all the decimals again. Whoop. Oh, it's because I multiplied it. All right, so I'm getting that blue y, okay, which I got by going 136.255 plus negative 60 is 76.0299. Okay, so just so that I can, sorry, I didn't write these down here. All right, so x, blue x, okay, I calculated by going 49.59, bless you, plus 86.01. Okay, so that was taking black x and adding red x. Okay, and then I calculated y by taking the 136.255 and adding to that the negative 60.23. Okay, so that again was black y plus red y. Okay, so that's how I arrived at those numbers. Okay, I've just calculated the two sides of my overall displacement. How do I calculate the magnitude of my displacement now? I'm looking for the hypotenuse. How do I get the hypotenuse if I know the two sides? Now I use Pythagorean theorem. Okay, a squared plus b squared is going to equal this. Okay, well, squared. But all right, so to get my overall displacement, it's the same as what we did yesterday when we were doing the perpendicular vectors. We now have two perpendicular vectors. So that'll be our 135.603 squared plus our 76.0299 squared, right? And then square rooted. That'll give us our overall resultant. Okay, and again, I'm making sure I keep all of my decimals, okay, because it's really important when you're doing this, especially when you're squaring stuff. Okay, plus, and then I'm just going to take the answer from the last calculation and square it, because that keeps all the decimals. All right, so I'm getting that my overall magnitude for my displacement is 155.46 meters. All right, so that's good. I now know the magnitude, but I also need the direction. Right? So to calculate theta, I can use any trig function I want. I've got the hypotenuse, I've got the other two sides, it's totally up to you, okay, which trig function you use at this point, because you calculated all of these numbers. If you screwed up, you screwed up. It ain't gonna make any difference now, okay? So you can use whatever trig function you want to get this angle. I always use tan because tan's my favorite. I don't know why. I'm a geek. I have a favorite trig function. It's just part of being a geek. You have to accept who you are, okay? So I'm gonna calculate theta by going inverse tan of the opposite side, which for me was the 76.0299, okay, and dividing that by the adjacent side, which was 135.603, okay? And here's how I know that. I just go back to my diagram and say, I'm looking for this angle, that's opposite, this is adjacent. Okay. Well, again, we're going to do significant figures here. I'm keeping all the decimals until the very end, carry them all the way through, and then round at the end. Okay, so we'll have our so second tan of 76.02990419 divided by 135.6029208. All right, so it's telling me that the angle there is 29.27 degrees. Okay, and the only direction there is going to be the same one they gave me. Above the horizontal. This doesn't have compass directions. I can't suddenly just apply compass directions. I wasn't given those. Okay, so now we got to check our significant digits. All right, everything in this question has 3 significant digits. So my answer can have 3 significant digits. So my final answer will be that the overall displacement is 155 meters at 29.3 degrees above the horizontal. Okay, is that a slow process? It is when you first learn it, but it's always the same. So the more repetition you get on this, the faster you will get. All right, by the time we've practiced this for a while, you should be able to do a question like that in about 5 or 6 minutes. Okay, realistically, because it's always the same steps. You're just plugging stuff in. How much would that question would probably be worth somewhere between 6 and 8 marks. Okay, I would give you a mark for the diagram, okay, because that's kind of your givens for a question like this. I would give you a mark for each X and Y component that you had to calculate. I would give you a mark for calculating your resultants, X and Y, and then for calculating your final answer. Okay, so getting your magnitude, direction, final answer. So between 6 and 8 marks probably. Okay, all right. That takes a bit of thinking. So you got 4-minute break. Then we're going to try some more like this. Okay, so I'll give you a 4-minute break to give your brain a little break. I want you guys to try questions 1 and 3. We're not doing 2 because it uses the rectangular coordinate system, which we don't use. Okay, so you got a hiker's displacement being 15 kilometers, 40 degrees east of north. We want to know what the north component of his displacement is. That is, if he does that, how far north does he end up? All right, and then for question number 3, you got a snowmobile traveling 65 kilometers at 37 degrees east of south. You're just trying to find out how far east it goes during that time. So finding X components or Y components, okay, based on the vector and its triangle. So you're going to draw the vector and its triangle, calculate one of the sides. Okay, so we're going to have a look here at number 1, because as is usually the case, it's not the math that trips people up on a question like this. It's the picture, which is odd because most of the time, you think the math should be the hard part, but it's actually the picture that usually gives people trouble. And everyone thinks, well, I can draw a picture. Well, Maybe, maybe not. Okay, so let's have a look at this one. It tells me that the displacement is 15 kilometers, 40 degrees east of north. What's my reference direction here? North. All right, so I draw a reference line that is north, and then I go 40 degrees east of that. There's my triangle. That's 40 degrees east of north. All right, this line is 15 kilometers long, and they want to know what's the north component of his displacement. Which side is that? Y or X? Y. Okay, Y is the north directed part of this vector. So the Y component then, or the north component, is which side of the triangle? It's the adjacent side. It's touching the angle. All right, so to solve for that side, I'm going to use which trig function? Cos. Yeah. All right, so I'm going to say that the cos of 40 degrees equals, okay, the adjacent side, which is y, divided by the hypotenuse, which is, not 115, just 15 kilometers. All right, so if I want to get that adjacent side, I multiply both sides by 15 kilometers. So I'll have cos of 40 times 15 equals my north-directed component. All right, so it says they go 11 kilometers north. Okay, because there's only two significant figures in that question, so our final answer would be 11 kilometers north. Okay, this is what they got there. Okay, that's it. That's all I had to do for that question. It was just asking, can you find the y component of this vector? That's all. All right, number 3, same deal. All right, so give number 3 a try, same deal. Draw the triangle, find what component it's asking you to find. All right, so again, tricky part, drawing the triangle. Okay, snowmobile travels 65 kilometers at 37 degrees east of south. What's my reference direction? South. All right, so I draw my reference line south, and then I'm going to go 37 degrees east of that. So something like that. Okay, so this will be my x, this will be my y. This is 37 degrees east of south, and this is 65 kilometers. They want to know how far east I'm going to go. Which side am I solving for? X, okay, because x points east. All right, is x opposite or adjacent? It's opposite. Which trig function do I use for that? Sine. Okay, sine calculates opposite with hypotenuse. I have the hypotenuse. I'm looking for the opposite side. I have the angle. All right, so the sine of 37 will equal the opposite side, which is what I'm looking for, x divided by the hypotenuse, which is 65. Okay, so that means that the sine of 37 degrees times 65 will give me x, or the east component of that vector. All right, so in this one then, I go 39 kilometers east. Okay, that's my x component there, 39 kilometers east. All right, so guys, that's the building blocks of the big mess that we did here. Okay, we had to be able to find these x's and y's. Okay, that's what we just worked on with those two questions, was finding x's and finding y's for various vectors. All right, that's the fundamental skill that is required for you to do a question like this. Okay, you got to find those before you can add them together and get your totals. Okay. That one's good. Coordinates. Okay, I would like you guys to try just question number 2. Okay, it's just like the big long example, right, that we did. Right, so you're going to have to draw the first vector, okay, then draw the second vector on its head, so head, tail to head, same as before, okay, and get your total. I'll give you a few minutes, and then I'll draw the diagram so you know if you're kind of on the right track with the diagram at least. Okay, let's just have a look at the diagram here, just make sure everyone's on the right track. Okay, the reason I always pick number 2 here is because this illustrates the importance of scale. if you do not draw this diagram to scale, the diagram will lie to you. Okay, that means you'll get done the math, you'll look at the diagram and go, oh, I must have screwed up the math. Okay, more often than not, when your math doesn't agree with what you drew it wrong. Okay, likely you did the math right, but the drawing wrong. So here's what we've got. Okay, we got a player who runs 15 meters in a direction of 15 degrees north of east. All right, so my reference direction is east. Okay, and they're 15 degrees north of that. So it's a pretty shallow triangle. Okay, 15 degrees north of east, and this is 15 meters. Here's X, and here's Y. All right, that's my first triangle. The second triangle is that we have a 13-meter vector, 5 degrees west of north. So my reference is north. Okay, when that's too long. Okay, scale is important, so that's obviously too long. Okay, and we're looking at 5 degrees, also a pretty narrow triangle. All right, so I can't even really draw like the 5 in there if I'm trying to show this to scale. Here's Y, here's X, and this is 13 meters long. Okay, if I don't draw this to scale, and I see oftentimes people do this, they draw that 5-degree angle and they're drawing the thing way over here. Okay, like I've got to make sure my diagram reflects what happened at least approximately. All right, that means my resultant then goes from beginning to end and can make a triangle like this one, or you can draw it over here. It doesn't matter which way. Okay, I just like to draw it so it's outside of the other ones. Okay, so this will be theta, this will be y, this will be x, and this will be the overall displacement. All right, so that's what your diagram should look like. Now you got to calculate some x's and y's.